sixth grade. All right, so this is going to start our first video of me reading our laws of motion stuff to you today. We're going to be on pages 216 through 219 for this lesson. So we're going to be looking at the laws of motion. So last week we looked at some characteristics of motion, and we're going to look at the laws today. So the first, second, and third laws of motion. The first thing that I want to kind of talk about here for a second, I want you to imagine you're the passenger of a car and your dad is driving. Suddenly, your dad notices that the car in front of you has stopped. Your dad slams on the brakes. So what happens to your body when your dad slams on the brakes? Well, your body is going to jolt forward when the brakes are slammed. If the driver of the car all of a sudden puts his foot on the gas and takes off, what does your body do then? Well, it jolts backward. All right, pushes backward. So these are because of the laws of motion. So we're going to be reading on 216. You can either use your book or you can read along with me while I have the book up on this video. All right, medieval scientists believe that all things tend to slow down and come to rest. Though these scientists made correct observations, their conclusions were wrong. Galileo Galilei discovered that contrary to what the scientists of his day believed, a moving object does not come to rest unless an outside force acts on the object. As Sir Isaac Newton continued Galileo's study of how and why things moved, he formulated the 3 laws of motion. So you might hear these called Newton's laws, and it's because they were formed by Sir Isaac Newton. All right, first law of motion. The first law of motion says that an object tends to stay at the same velocity unless another force causes it to change. An object at rest, 0 velocity, tends to stay at rest. An object traveling in a straight line at a constant speed tends to keep on moving that way. All right, so if something's not moving, it will stay not moving unless something makes it move. That's what that's saying. The resistance to a change in motion is called inertia. If you have ever been in a car that stopped, suddenly you experienced inertia. You were thrown forward in the car because your body was in motion, and it stayed in motion even after the car stopped. When you push someone on a swing, it is harder to get him started than it is to keep him going. You must first overcome his body's tendency to stay at rest. Velocity involves not only speed, but also direction. If you have gone into a tight spiral on a roller coaster ride, you know that your body wants to go straight, even though the track turns. You feel like you were being pushed to one side. Perhaps you have swung an object on the end of a rope, round and around. When you release the rope, the object goes in a straight line from the point that you let it go. It does not continue. Oh, sorry guys, I switched the page. It does not continue sorry, I lost where we were. It does not continue circling. Obviously, objects in the universe do not keep hitting the wrong thing, guys. I'm so sorry. Obviously, objects in the universe do not remain still or keep moving in straight lines. If you jump up to shoot a basketball, you will not continue floating into the air. If you roll a toy across the carpet, it will roll for a while and then come to a stop. Certain forces are operating against inertia. One force that keeps an object from moving indefinitely in a straight line is gravity, the pull of one object on another. Objects with greater mass have stronger gravitational pulls. Since the Earth has more mass than anything on it, it pulls objects toward itself. If you throw a softball through the air, gravity will pull the ball to the Earth. At the same time, the ball pulls the Earth toward itself because the mass of the Earth is so much greater than that of the ball. The pull of the ball on the Earth is very, very tiny. When we talk about mass of an object, we're referring to the amount of matter in that object. However, when we talk about the weight of an object, we're referring to the gravitational force on that object. So weight is actually a measure of force. An object that weighs less has less gravitational force being applied to it. For example, you would weigh less on the moon because the gravitational force pulling on you would be less than that on Earth. All right, so yeah, we kind of don't always understand that. Your mass would stay the same whether you're on Earth or the moon, but your weight would be different because of the gravitational difference. All right, friction also works against inertia, and it's helpful in many ways. Without the force of friction, you would not be able to walk. Your foot would not be able to grip the floor and push you forward. Without friction, turning over in bed or stopping your car would be impossible. Sometimes people increase the friction of surfaces. Rubber cutouts stuck to bathroom floors increase friction and keep people from falling. Baseball players wear batting gloves to keep their hands from slipping on the bat. Rubber tires give more friction against the road and help a car from sliding on the road. In other situations, friction is not helpful and people try to reduce it. Winter sports such as sledding, skiing, and ice skating are fun only when there is less friction. Snow skiers wax their skis to reduce friction and to allow the skis to glide quickly along the snow. People put lubricants such as grease and oil on machine parts to reduce friction on the parts that rub together in movement. So as you can see, sometimes friction is beneficial, sometimes it is not. Fantastic facts. Air resistance is an example of helpful friction. If raindrops meant no resistance, they would be falling faster than the speed of sound by the time they reach the earth. Rain showers would be painful indeed. Gravity pulls the drops earthward, and air resistance limits their maximum speed. The two forces soon balance each other, and the raindrops fall at a constant speed. This is why God had to think of everything so rain wouldn't kill us. All right, let's look at the second law of motion now. All right, most of us recognize that moving a 50 kilogram or 110 box is easier than moving a 500 kilogram or 1,102 pound box. Okay, obviously, right? So Newton's second law of motion states that force is equal to an object's mass and the acceleration of the object. The following formula illustrates the second law of motion. So mass times acceleration equals force. Several principles result from this formula. First, the greater the mass of the object, the greater force needed to move it. For example, a little bit of force can move an empty cardboard box, but moving a cardboard box filled with encyclopedias requires much more force. Moving a golf ball with a golf club is quite simple, but moving a bowling ball with a golf club would be quite difficult. So, again, like the mass of the object needs, the bigger the mass, the bigger the force that's required for you to get it moving. Another principle we can derive is that the greater the force exerted on the object, the greater its acceleration will be. Athletes use this principle often. The harder you swing a tennis racket or baseball bat, the faster the ball accelerates after you hit it. You can also conclude from the formula that the greater the acceleration, the greater the force exerted on an object. That this is why it takes more force to throw a fast baseball pitch than to throw a slow baseball pitch. The fastball has more acceleration, so it requires more force. All right, third law. The third law of motion is sometimes called the law of action and reaction. All forces come in pairs. When one object exerts a force on another object, the second object reacts by exerting an equal force back on the first object. For example, a person paddling in a kayak pushes the paddle backward against the water, and the water reacts by pushing the boat forward. The boat moves in the opposite direction of the force of the paddle. If you sit in the chair that has wheels and push against your desk, the desk pushes you backwards. All right, so this basically, like, sum this one up, is for every action there's an equal but opposite reaction. You've probably heard that before. If you've ridden on a bumper cars at an amusement park, you have felt Newton's third law of motion. As you bump into another car, the other car bumps you back with an equal amount of force. Rockets ascend because of Newton's third law. As the rocket expels gas, right here, what happens to it? Well, the gas goes down and an equal and opposite reaction occurs. The gases exert a force that causes the rocket to move upward. All right, so let's look here at the boat example. So you see that the paddles are pushing the water backwards, but it makes the boat go forwards. If you constantly push the paddle backwards and you just kept going backwards, that would be kind of pointless. So, all right, so those are your three laws of motion. I'm going to really quickly look at this next thing. You're going to have a paper coming to you that has some it says this cars in motion activity that's in the stuff that I sent your parents. And this is what you're doing with it. So you basically, I want you to use cars to demonstrate the laws of motion. So you can use, like, find some toy cars around your house, and then you can use anything else around your house to make the first law, second law, and third law. And basically you're drawing a picture of what is going to happen. The box on the paper, if you have that out and you look at it, the box on the paper wants you to say what materials you used, write down the third law, what is your plan, and how was it successfully demonstrated. So just draw like a picture of what your cars did so that you could show those laws. That's all you're doing. If you don't have cars, just use anything that you could hit against each other so that you could see it working. You could use ping pong balls, or I mean, you could use basketballs. You could use any kind of a ball. Anything that rolls would be a good way to use this, but toy cars are more fun because you can make it like car accidents. So anyway, all right, so that is your first lesson. I hope you guys have a good week trying to finish off this stuff. If you have any questions, you can scroll down to the bottom of this video and you can type in your questions, and I'll try to get back to you on that. And you also can text or email or call me as well. All right, have a great afternoon.